Okay, I think we're live on YouTube. Hello to the people who are here on YouTube, and hello to everybody who's in the room as well. We're having another amazing empowerment day this evening for the Black Coder Bootcamp, and we're really, really excited because we're going to have Tessie giving us an introduction to computer science. But before we get started, I'm going to give you a little introduction to the Black Coder Bootcamp and all the amazing stuff we're doing. So the Black Coder Bootcamp is a new bootcamp that has been created for Black women to get into the tech industry and become full stack developers. It's a fully funded bootcamp and it's part-time over a 30-week period. So we're halfway through at the moment. We're just covering databases and it's really exciting, a really exciting bootcamp, loads of amazing women, most of which are on the call this evening, which is amazing. And we're really excited about the rest of the journey that we're going to have. Everyone's about to start their projects, so we can't wait. The bootcamp is run 2 evenings a week over 2 cohorts. So that's Monday and Wednesday and Tuesday and Thursday. We also do empowerment days, which are for attendees to attend and for external members to come along as well. And that's to give people a chance to be empowered and be inspired about the tech industry and to find out more about it as well. So as I said, we've been fully funded and our main sponsor is the West Midlands Combined Authority. They're really, really keen to make sure that we can enable more people to gain access to digital skills and to get into the tech industry. The Black Coder Bootcamp is a bootcamp that's been created by Coding Black Females and Neo Enterprise. One of the founders, Oyen, who is on the call, she's from Neo Enterprise, and Laulu, who I think is here as well. I think I saw her pop in. She's the CMO at Neo Enterprise, and I'm the founder for Coding Black Females. So we brought together 2 amazing networks to put together a fantastic bootcamp, which is the first of its kind. And we are the women behind it. So we put together this bootcamp, we're building an amazing program, and it's great to have you all here this evening to find out about computer science. I'm really excited. Woo! I'm going to stop sharing and I'm going to hand over to Tessie. So Tessie, if I'm correct, you are the head of computer science at the school that you work at in Birmingham. And Tessie will be delivering for us this evening an introduction into computer science. Computer science is vital for what we need to know about technology and how we're going to be in the tech industry. So we're really excited to have you here this evening. And clearly it's a very popular topic as well. So thank you very much for joining.
Thank you so much.
Thank you. I'm going to hand over to you now.
Okay. I hope everyone is as excited as I am because I love computer science and I hope the passion shows through. Bear with me for some of the things I'm trying today. I've seen them used, so I wanted to try them, such as Jamboard. I'm going to share my screen. If I'm going too fast at any time, just tell me to slow down. I think I'd rather go away with everyone picking up one objective to do it well rather than rush through it and nobody knows what I'm talking about. So if any time, pop that in the chat box. So let's begin. I'm going to share my screen and just let me know if you can see it.
Yes, oops. We can see your screen.
Okay, and I need to present it as well. So here we go. Brilliant. Can you all see that?
Yes, we can.
Fantastic. So this is Introduction to Computer Science, and it's basically a journey of how computers work. I'll do a really quick intro about myself because I'm mindful of time. If we have time at the end, then I will say a bit more. So my name is Tessie Masindi. Like Charlene said, I'm head of computer science and business at a secondary school in Birmingham. I'm new to teaching, actually. I only joined in 2018, and I saw there was a big gap in terms of Black women in general teaching computer science, then Black women, and furthermore in a leadership role. So as soon as I stepped in there, I said to myself, well, I want to fill that gap. I want people to see me. I want to be visible. I did this session especially because I'm self-taught in programming. So I don't actually have a computer science background. I picked it at uni, and I thought it was a bit boring because I was just being a brat, so I dropped out of it. So my degree is actually in international politics. So this was just to encourage people that it doesn't matter what your background is, you can still come back and learn those basics. I did a lot of work in tech startups. I initially started an online platform for African entertainment professionals. So that was my first foray into tech startups. And then I had an on-demand app for handymen. And then I started a online fashion retail to connect fashion designers in Nigeria, Africa, with consumers in the UK. So that was a lot of fun as well. I got to do the catwalk and everything. Now I've dialed things back, because when you come into teaching, you realize you ain't got time for nothing. So now I just do Educating Africa. It's a charity that supports disadvantaged girls, Afro-Caribbean girls, to go to school. We've got 4 girls at school now in our cohort. We're looking to build bigger. We're trying to do a computing hub. So I just focus on little things at a time. Fun fact is, I used to be an Afrobeat singer. So if you've heard about Wizkid or Tiwa Savage or Burna Boy, any of those, I was kind of there before they started, and I've seen it grow really big. So yay me. Let's move on now. So these are the big questions. Hopefully this works. I'm going to pop a Jamboard into the chat. And what I want people to do is to go on the Jamboard. I'll demonstrate in a minute how it works. If you've used it before, great, just go ahead. And in the sticky note, answer these questions. Please put your name with your answer. So when we look at them, then I can see who said what. I'll give about 5 minutes to make it fair in answering the questions, because it is quite a bit of questions. Please attempt as many as possible. If you only know a few, fine. If you only know one, okay. If you know all, go for it as well. So I think I do that by coming out of this and coming into the chat. Oh, coming into Zoom, sorry, done it wrong. Is that working? No. No. What am I doing wrong? Wrong
Is there
one.
anything that I can do to help?
No, it's all right. I think I just need to get into the chat. How do I get into that? There it is. That's it. I've got the chat. It was at the top. Don't mind me. If I can do that and I'm a computer science teacher, then there's hope for everyone. So just click on that link now. I'm going to go to the Jamboard myself and show you. So you just click on the sticky note. It's got different colors. And if you just put your name, like I'm doing here now, and you can type the answers. I'm going to come out of it, so then I can leave the answers on there. And if we say 5 minutes starting now. Yeah, so the first question is, are computers smarter than humans? And that can be yes, that can be no, depending where you lean, but explain why, because we just don't do any questions where we don't explain. We need to challenge ourselves. How do computers communicate? What is von Neumann architecture? Do not Google it. What is Moore's law? And then we've got a spiritual, moral, social, cultural question, which means just tying back to the environment and the communities we live in. What is the impact of computers on the most disadvantaged communities? When I say disadvantaged communities, I'm talking about low-income earners across board. They might have different circumstances, but still those in the below the poverty line in whatever country. So it could be in the UK, it could be in India, it could be in Poland, it could be in Africa, Nigeria, etc., Ghana. I keep saying Nigeria because I'm from there. I apologize. It could be Jamaica. So wherever you think, what is the impact of computers on the most disadvantaged communities? I'm going to go stop talking now and give you guys a chance to answer. Let me just mute myself so that way. Oh, should be up here again. I need to learn that this thing is up here because it doesn't come out for me. There we go. So I'm going to start looking at people's answers. I did say 5 minutes, but I'm just being quite aware of time as well. So let me just come out of here. I'm still sharing. I want to keep that there. Move this one and go onto the Jamboard and see what people have written. Oh, a lot. Yes, this is good. Okay, this is really good. Okay, just want to encourage as many people as possible. Don't be shy. Just pop your answers onto that Jamboard. Oh, there's a second page. Let me have a look. Okay, nothing on the second page. As many people as possible. Very good. It's just got 1 minute left. Okay. And 3, 2, last one going up. 1. Fantastic stuff, everyone. If we want to just stop typing now, I'm going to pick a few based on the order of questions. So our very first question was, are computers smarter than humans? Yes or no? Why? So let me look at some of the answers. So we've got, I don't believe they are. Humans created computers and wrote instructions for the computers to follow, said Jay. Okay, quite good. Someone said yes and no. Computers are smarter in terms of AI and maths, but humans are very smart because they are the brains behind the computers. Good effort as well. Very well done. Okay, this is still, computers are smarter than humans. The programs on computers are written by humans, so they're dependent on the humans. Very fair point as well. I'll play devil's advocate because I didn't see a lot of devil's advocate ones, which I always get from my students, where they say, yes, human beings make the computers, but when they built them, they become smarter because they learn quickly. And one of them made a really good point today. They said, for our generation, all we do is learn from computers, miss. So just playing devil's advocate on that part, a lot of younger people feel that computers are smarter than humans. I know we as adults, we understand that we program computers and it makes sense. We're the ones that write those programming instructions. Second one, really well done, guys. How do computers communicate? Someone said computers communicate through networks. I'm going to zoom this in so everyone can see. Zoom it right in. Can I come in? So who said that? Nina zoomed 2 in. So Nina said, computers communicate through networks using encoded messages. Okay, do I have anything else? By sending data to each other in small packets via networks. Okay, quite good. Anyone else that said something? No, I think that was it basically. And then we have, what is von Neumann's architecture? Did anyone answer that? Let me zoom out a little bit. Don't see von Neumann's architecture. No, not there. That's fine. What is Moore's law? Not sure anyone answered that either. And then what is the impact of computers on the most disadvantaged communities? So someone said computers are expensive. Not everyone can afford them. Anything else? Having access to computers in disadvantaged communities can empower and give these individuals a voice, especially younger people. They can have an outlet. Don't know who said that. That's a really good answer there. Some of them don't have names to the answers, I understand. A bit anonymous, that's fine. So I just thought that would be a nice icebreaker into the topic, because not only do we have to think of all the technical aspects of computers, but like I said, in the environments that we live in, the environmental impact. I think we focus a lot on the positives, which computers have a lot of positives, but the environmental impact, such as how they're disposed of or how the resources to make them are gotten, we rarely focus on that aspect. So when you do computer science, you will then look at that in a little bit more detail. Okay, I'm going to move on then. Again, like I said, a bit mindful of time. To the objectives, because I am a teacher and we have to share the objectives so we know what we gain out of being here. So the main one is we need to know, let me minimize this out of the way. We need to know the principles of von Neumann architecture. So at least to hear a bit more about it today. You might not know it in its entirety, but you will know a bit more. And we need to be able to explain the functions of the CPU, that's the central processing unit. We need to be able to discuss stages of the Fetch-Decode-Execute cycle. We should know how computers represent data. And the big one for me on the maths part is to be able to demonstrate converting binary to denary and vice versa. If we leave here with all of these, or at least one or two, quite happy with it. The challenge is to know how to discuss the difference between low level and high level language. As we said, some of you are in a boot camp, you're dealing with a lot of high level language. Everything connects together. So why are we here in the first place? Why is this important? Well, like I say to some of my students, there's no point trying to be, say, a chemist or a scientist without knowing about atoms and protons and compounds, chemicals. You need to know at least chemical equations. And that's the same thing here. There's no point us learning data science and all the best programming languages if we don't understand the foundations of computer systems. So it all links together. So what is a computer system in the first place? If you've got an idea already, drop it in the chat anyway. I won't be able to stop and read them, but drop it in the chat anyway, and then I'll go ahead. If you've got an idea already, I'll take 30 seconds before I put the next slide on. Fantastic. So a computer system is an advanced device because it takes a set of inputs, for example, from a keyboard, from a mouse, from a microphone, if you're a singer. It processes them, meaning it makes sense of it. It looks at it and says, well, what is this? I don't actually know what does this mean? Okay, it's a mouse click. And then it produces an output in the form of on your monitor, on a screen somewhere, speakers, etc. And these instructions are stored, and the output could also be stored. You would be surprised to know a lot of these concepts are quite recent. So this hasn't been since the 1800s or anything. As recent as the 1940s, these devices did not exist. So that's the diagram there. We take an input, we process it, we store the instructions for it, the data, the instructions, we output it. And what is the name of the component that is the brains of the computer? What is its purpose? So as human beings, we have our own brains, and we use that to sort of think, we calculate, we carry out logic, all with our brains. The computer system also has its own brains. So you can drop that in the chat as well. What is the name of the component? What is its purpose? If you want to join in and talk about it, I'll be very happy for you to as well. 30 seconds. Can I see the chat from here? What people are saying? Not quite. No. Okay. I can actually look. You see chat. Guessing the CPU, but don't know how it works exactly. CPU, fantastic job. So it is the CPU. It is the brains of the computer, central processing unit, and it's in all the computer devices that we use. And when we say computer, especially to the younger children, they see a computer, which is actually laptop sometimes, a desktop, and they start tapping the screen because it's not a phone, because in their minds, everything is about phones. So even the phone has a CPU. It carries out all the logic, it carries out all the calculations, it's got a lot of instructions that it carries out to make the system run. Without it, which is why we're here again, there is no computer. The first thing I say is, take your phone out. You don't care about the CPU, go dash it in the bin. Simple, because that is the foundation for now. None of the concepts have changed too much since the 1940s, where a lot of this started. And that introduces us to von Neumann architecture. So von Neumann, he's a computer scientist. He thought to himself, he's looking at all the architecture that's in place. Specific tasks were done by specific machines. So for example, you want to listen to Drake. Okay, just that process to say, is this Drake? There would be a specific machine built as big as a room, and it could only carry out that specific task. So von Neumann thought to himself, his name is John as well, in 1945, he thought of this concept that actually, rather than build big machines, why don't we build programs? Why don't we store the data and the instructions in a place called memory? Why don't we use the processor to process, the central processing unit to process these instructions, and then we can collect that output and collect the input and produce an output. Okay, there are different types of processors. Today we're just focusing on the central processing unit because that's vital. So the von Neumann architecture, like I've said, is the idea that data and instructions are stored in memory. They are fetched by the CPU. That CPU controls the input signals, processes those instructions, and produces an output. And this is what we call von Neumann architecture. So we've got the first objective out of the way. Yay. So still thinking about von Neumann, like I've said, before 1945, we had a primitive way. We just put computers there, build a big machine for a specific task. But now, as we know, different programs can be run to do various things, take your pictures, make a video, record a song. Because of the programs we've built, we can have multi-purpose computer systems, okay? So when we've got those instructions stored in memory, then the CPU has to fetch them. So it's got to go get them, it's got to decode them, and it's got to execute them one at a time. Doesn't go beyond one at a time. And a lot of people are confused because if it's one at a time, how come it's so fast? So we'll go into that in a little bit. And the components in the CPU that carry out these stages, we're now on the fetch, decode, execute. So that means we've taken an input in. We need to make sense of it. It's come from a keyboard, it's come from a mouse, a microphone. To make sense of it, we need to go get those instructions. So the whole component doing that part is the central processing unit. And this is the fetch, decode, execute cycle. The main components we'll look at today are the control unit, the arithmetic logic unit, and the registers. And the way I try and make my students relate with it, I said, think about a band, the best band in the world, Destiny's Child. That's the CPU. And these are the components, the band members. Got Beyonce, Kelly, and Michelle, bless her. She always has to be the last one. So basically, if we've got those band members, and that's what we've got here in the CPU, they all have their purpose, they all have their role to play. So the most important component, I would, in my opinion, is the control unit. The control unit is the center of operations. If you're not really into music, I also think about being in a spaceship. I watch a lot of Star Trek or Stargate. You see that control room, the command center, where everything, all the switches and the lights are going on and off. That's how the control unit works. It manages the signals from the input and output devices. It tells the ALU what to do. Yeah, it's boss, so it's telling the ALU, it's managing all the parts, it's fetching those instructions, it's decoding them as well, and executing them in certain cases. And then we've got the Kelly, the arithmetic logic unit, carrying out all the calculations, adding, subtracting. If you think of Tony Stark in Iron Man, he's always doing all these calculations and he's making this decision. Should we harness vibranium? Should we not? Should we kill the aliens? Should we? That's what the ALU is doing. It's carrying out Boolean logic. It's carrying out all the calculations, specifically calculations. So there is a difference because people ask, when I press A on my keyboard, what happens? That's slightly different from when you type 5 times 5. There's a little bit of a different process there because any calculations, the ALU will handle that. So we know those two parts. Next special component are the registers, and they are very, very important because they are memory stores. All they do is hold some memory locations or hold some instructions. They don't actually deal with it, so they don't execute it, they don't decode it. Think of them like a mailbox in a way. They just store little bits of information. And there are 5 main registers: the accumulator, the program counter. The program counter just collects the specific address and increments it. We won't go into too much detail for now, but I just want you to know these main registers. So the accumulator, program counter, memory address register only stores memory addresses, current instruction register, which stores the current instruction, and the memory data register. This is all still in the fetch, decode, execute cycle. It's crazy. How is this all happening really quickly when there's a lot going on? And I've designed a beautiful city for all of you to see today, just to imagine this whole process going on. So we've got the RAM there. Random access memory is the main memory where the instructions and the data are stored. Got some little bits of instructions there and the addresses too as well. I've also got all the registers. I've got the CU there and the ALU, and you can see that I've got lines going across. So these are buses, so they transport. So in real life in the city, we get on the bus, you get on the bus 74 or whatever bus from town. There's the same thing here. We've got an address bus specifically transporting addresses. We've got a data bus transporting data. We've got the command bus that talks to this really important CU. So I'll just let you look at the city for a little bit. Got any questions you want to chip in, you can do that now. I'll just pause for 30 seconds so we can look at all the parts. We've got the accumulator right at the end. The accumulator is like a warehouse. So it temporarily holds the instructions as well. So all these little parts play their role in making sure that our cycle from input all the way to output is being run. 8 seconds. I hope I haven't lost anyone yet. I'll look in the chat and see if anyone's like, no, stop, I have a headache. Oh, yes, I've answered it there. Okay, that's fine. That's fine. Okay, sorry, I've taken away your beautiful city back here. So that's the city. I'll send all of this to Charlene anyway. Now we need to go a little further in to talk about RAM and ROM, because we need in this architecture that von Neumann's come up with, he has said memory is a main part of it, okay? Because we're storing instructions, we're storing data. So there are two types technically, but 3 types of main memory, and that is read-only memory, okay, and random access memory, right? Read-only memory is a library where you can only go there to read. You can't rewrite it. Once it's been programmed, it's very hard to change it. This is just for the boot up sequence. We don't fetch instructions from there. So even when the boot up sequence is running, we will temporarily take that instruction and put it into the random access memory, which is where all the instructions or data are being fetched from. And then we've got the cache, because there's a lot going on with RAM. RAM is being pushed on constantly, storing data. So there's a cache that sits on the CPU as just a temporary store of open programs. So that way, as we're running, if there's something we're already doing, there's no need to, imagine taking the bus all the way to RAM. You don't need to do that. If there's a program that's opened over and over again, the cache will keep it. So instead of traveling on that bus, that data bus, back to RAM, it can just travel within itself, in its own street to the cache and go and get those sets of instructions. So it's actually called a bottleneck, the speed in which the processor can work and the amount of instructions that can be fetched from the RAM at a time. So that cache was put in place, and cache has become so advanced now. There's layers of cache, and that's what will actually affect the speed of your computer. Let me keep it back on this one. When we talk about the speed of your computer, a lot of people just look at the gigahertzes and look at the RAM and know there is a lot to go with the cache and now virtual memory. I won't confuse people, but there's another technique now to try and make the computers run faster, okay? So I'll pause again. So with main memory, with primary memory, without it, your computer cannot run. Okay, so this is not secondary storage. You don't need a hard drive. You don't need a solid state drive. You don't need a floppy disk. You don't need any of that. What you actually need is your main memory. You won't be able to store all your cool pics and videos, but at least you need your computer to run fast. Okay, so this is the idea that as a human body, this is the minimum, the bare minimum you need for it to work. And coming to then relating that to what a lot of us are doing, we're focusing on programming a lot. The thing is that whatever we're programming is actually a high level language in that humans can understand it. What the CPU understands is machine code, which is a low level language because it's closest to what the CPU knows. So when I asked earlier, how does the CPU communicate? Well, it only understands zeros and ones because of electrical signals. So we're flooding a lot of electrical signals at any one time. This is called machine code. But even then still, human beings can't read machine code. So we have to have some kind of assembler. So it's called assembly language, where it's really basic, but we can talk to the CPU directly. So you'll see I've got that assembly language there. Depending on time, again, I'm checking, oh, we're good, we're okay. We might look at that assembly language and just have a little play with it. We'll look at what we call little man computer. So the assembly language has an assembler to convert that language into zeros and ones, because all the computer knows is 0, 1, 0, 1, 0, 1, 1, 1, like a little band of 0, 1 singers. When we code in high level language, then there's a compiler or an interpreter that then converts that code. Imagine we put, if some people might have gone advanced or not, but if you set a variable and you say x equals 2 plus 5, print x or whatever, the computer, the CPU does not understand any of that, only we do, okay? And this is sort of an example of assembly language because all CPUs have an instruction set. So it's a very brief, short set that does very basic things: subtraction, addition, loading the instructions, storing values, branching out to a different part of the program. Just let you have a little look at this instruction set. I'll check if there's any questions. Okay, someone said, wow. Is that wow as in a good way, or I hope it's wow in a good way. I hope I haven't lost anyone yet. So this is the instruction set. Everything is, yeah, go ahead. Someone was talking. Is it me? No? Okay, I thought someone was about to speak. So let's have a look at Little Man Computer. I'll put the link in the chat if I'm able to pull it off. I'll show you what the instruction sets look like that we're going to type in. I'll leave it on the screen, but it just simulates how the Fetch-Decode-Execute cycle works. It shows you all the little registers as well in action. So that'll give people a chance to just try it on their own. I'll give a timer as well so you come back. Let me pull it out. So this is what it looks like. We type in this bit here. If we were in a live lesson, well, in the classroom, I could show you everything on a board or whatever. I can still try and type it here, but I want you to see the instructions. So we've got the code there, we've got the output there, we've got all the little, we've got the RAM there, and we've got the registers on the left, we've got the program counter, everything's on there for you to see for yourself. So all I've said is not just abstract, because computer science has a lot of abstract information and people can't connect with it. If you give me a minute, let me just get that for you. Here we go. Put that in the chat so everyone can have a go. Where's my chat gone now? Yeah, there we go. Great job. Okay, so everyone click on that link. I will leave you a few instructions to try out. Let's say is 5 minutes, no, 3 minutes. Let's make it 3 minutes to be fair. Try out some of these instructions and then see how you feel. Someone said something. Let's have a look. Oh, fantastic. Thank you so much, Inkem. And you're my namesake as well, because I'm also called Inkem. So thank you so much for that. Let me put that back. Okay, so we're going to write a few instructions. I'll put them on the screen. Go ahead and try some of these. So instruction 1, try some of these. In a way, you can call it a break as well if you want to go loo quickly. And anyone who tries it, can you just pop in the chat that you've tried it and what you saw, what you found? 3 minutes starting now. Okay, someone said, I'm not clear on the task. Oh, I apologize for that. We usually do thumbs up if you know what you're doing, but because people's people's cameras are off, basically it's going to, Melanie, the link, the Peter Higginson link. It's got a little man computer, and that little man computer, it looks like this, basically. So it's simulating how the CPU works. It's simulating how the instructions are fetched from the RAM when we write the program. So we're writing in assembly language, but it's actually communicating with the CPU. So just simulating all of that. That's what the task was about. I can see some people did do it, and I had left some instructions. I can give one more minute, so we try these instructions. Someone said, let me see what's here. Why does this, there we go. Someone said, okay, shows how the numbers are fetched and processed by the CPU, and finally how, yes, it does. Everything seems to be originating in the CPU, yes, and either going to the arithmetic unit and or RAM and then back to CPU. I'm not sure why some of the data bundles are, I assume that's what they are red and some are blue. Okay, I'll answer that as well. But yeah, every description here is absolutely correct. Yes, everything's originating in the CPU. You've got to obviously go to the RAM to fetch those instructions. If there's nowhere to store the instructions, then there isn't really a von Neumann architecture in the first place. Okay, so it doesn't work without that RAM aspect. There were a few instructions I wanted us to get through, but we've already done about half an hour and there are 2 more sections. So I'm going to take a breath. It's a lot of information. I will send a PowerPoint to Charlene so you can try out some of your own little man computer tasks. I've put a few tasks in there like we would do normally in a live demonstration. So I'm just going to move on. We've done our simulation. So we've done the first learning objective. We wanted to know about the von Neumann architecture. Let me just look at those objectives again, so we know we've made good progress. Got a few. So we had know the principles of von Neumann architecture, be able to explain the functions of the CPU, be able to discuss stages of the Fetch-Decode-Execute cycle. And so I'm going to bore you a little bit with that, but it excites me. Then we move on. So the Fetch-Decode-Execute cycle is actually what happens when our instructions, I'll actually go back to the slide as well, so that way everyone knows what I'm talking about. What's happening in this city here. So in the fetch phase, the CU sends for the instructions to be fetched from the RAM. So that's what happens in the fetch phase. We're just fetching the addresses, fetching the instructions. I'll just keep it simple like that. That's what happens in the fetch phase. A lot more happens with the program counter, the memory address register, and the other registers, but we won't go into detail with that. We just know that in the fetch phase, instructions are fetched from the from RAM. Okay, in the decode phase, the CU, the control unit, is looking at those instructions and making sense of it. It's decoding it. So for example, if you were speaking another language, you'd have to look through and translate. So that's what the control unit does then. It decodes those instructions. And when it realizes what the instruction is, it could be load some data. For example, it says load 3. If we type these in our assembly language, it says load 3. So it's going to look in 3, address 3, and see that in there is 5. So it's decoding those instructions. And then in the execute phase, it's going to decide what part. Is it the ALU? This looks like numbers, so that's going to be the ALU. Is it some logic? Well, that's going to be the ALU. If it's anything else, the CU will take care of it. And then it will execute. When we say execute, we mean carry out those instructions. So that's what we mean by when we say fetch, decode, execute cycle in basics. That's what it's about. It's a little bit more detailed when you throw in the registers. Got a question here. Okay, just someone dropping in. Fine. It's a little bit more detailed. Does anyone have any questions about this section at all? Because I'm about to move onto the maths crunching numbers part. We're basically going to look at how data is represented. So if any questions, just drop them now. All the way. 30-second pause.
There's one question in the chat.
Oh, okay, let me have a look at it. When would you need to use the assembly language? Good question. When you're communicating with the CPU, only then. If you're writing high-level language, it will be compiled or interpreted straight to machine code. So it's when the CPU is being programmed, the instruction set of it. So Intel, probably programmers that work there, they are the ones, because they have to program the CPU. They would use assembly language, not me anyway, because I do Python and JavaScript, and those are the ones I do. But those are the instruction sets that they would use, because they don't code in zeros and ones. Thank you for that question, Nina. Any other questions at all before we go on to how computers represent data? Okay, fantastic. So we've done our simulation. We know how the Fetch-Decode-Execute cycle works. Now we need to go in depth to think about how computers actually represent all these tasks we want it to do. We want it to play. I want it to play loads of Afrobeat all the time. I'm programming as well. At the same time, I'm sending an email, storing pictures. We're doing so many things at once. So how does it recognize all this data when it only speaks electric? So humans are so amazing. We've forced an electric device to know what we want, basically. So inside the computer, we already know that there is a CPU. This CPU has millions of tiny switches known as transistors. It also has circuits. So we know switches, for example, the light, you can't see my lights, but they're light switches, for example, they only go on and off. There is no halfway switch. Even if a light is dimmed, it is still on. So it's only on and or off. Those are the two states that it knows. So on that basis, then, I'm trying to give you a visualization, because the CPU might be a bit abstract. I would say pick up one. If you've got an old computer lying around, you will see the transistors. You will see the chip as well. You will not see the circuit or the logic gate. These are abstract still, but these are the layers on the CPU. You've got the chip, circuits, logic gates, which we'll look at in a little bit, and transistors. And these transistors, they only, some of my slide is missing. Okay, I'll go without it. They only recognize two states, on or off. 0 means off. 1 means on. So on or off, 0 or 1. But human beings, if we look at our hands, just stare at your hands. I know not everybody has the same fingers, but imagining we all have 10 fingers, then you can count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice we always start at 0 when we count. So that way, the other numbers are actually just a combination of these 10 numbers. There are no new numbers after 9. Everything is 1 and 0, 1, 0, 0, 2, 3, 4, 5. It's all combinations, and then we can count unlimited. Will this number system, it's called the Denary number system or Denary number system, in which humans count. It's also known as base 10 because we count 10 numbers. Will this number system be appropriate for data representation? If the computer only has two states, 0 and 1, can I challenge someone to come onto the microphone? Because it feels strange with only me, no one answering as well. I always have people in the classroom commenting. Can someone come onto the microphone and explain why they think this will not be appropriate for data representation?
I'll jump in. Hi, sorry, I'm not going to turn my camera on.
That's fine, Charlotte. Thank you for jumping in.
But does it have something to do with, so if the computer can only count in zeros and ones, so it's got two numbers to choose from, if you're thinking of counting in powers of 2, that might be fine, but 10 isn't a power of 2, so that doesn't really work out so well. I'm sure someone has a better explanation, or you'll be able to explain it probably, but
fantastic. Carry on.
Oh no, I was just gonna say that might be one of the reasons. There's probably more.
So that's the main reason. It only understands zeros and ones, which is powers of 2. So very well done, Charlotte, and thank you for jumping in there. It means I haven't lost everyone. If I've got one person, that's good enough. So when we try and go above those powers of 2, there will be an issue. So that's why with the computers, we have to look at binary, we have to look at base 2. So thinking still of Denary, we count in hundreds, tens, units, thousands, because we're going in multiples of 10. So if we look at the units section, we have no tens there, it's just ones. And then we look at the tens section, we have 1 10, and then 2 tens at 100, which is 10 times 10, and 3 tens at 1,000, and that goes on and on and on. That's how we count. And if you notice as well, we've got it increasing from right to left. So in binary as well, if we add this up, it all comes to, this is not 9,000, this is 9,928. So we've already said this, 0 means off, 1 means on. And in the binary system then, which is what we use, zeros and ones are what we have in them, only 2 numbers, like Charlotte said. So the binary system is what computers understand. The Denary system is what humans, well, one of the systems humans understand. So we have to bridge that gap between human and CPU. So each 0 represents a bit. We call each 0 a bit, each 1 a bit. 8 of those make a byte, not a McDonald's byte, but a different type of byte, B-Y-T-E. And these bytes are what we use. We usually use 8 bits to represent numbers, letters, etc. Sometimes we have 4 bits, we call that a nibble, okay? Where else have you heard the term byte? Just drop it in the chat. What else does byte relate to? Where else have you heard those terms? Byte, kilobyte, megabyte. So drop it in the chat. Where else have you heard that term? Yeah, in memory, in storage, yes. So we call this units of storage. Very well done. So where we have kilos, milliliters, liters, we also have units of storage when it comes to the computer system. It's coming back to that now. So like I said, we had our powers of 10, all multiplying as we move from right to left. Same thing with binary. We would have our bits. So we've got our first bit here, second bit here, third bit, fourth bit, 5th, 6th, 7th, 8th. I would advise you now in this section, quickly, go get a pen, go get a paper. I've got a mini whiteboard. It will be quite tough for you to do it without this unless you've done it before. I can do it without, but I'd advise you, if you've not done this before, get a pen, get a paper, so we can do some binary conversions. So we're looking now at how numbers are represented in binary. We're going to convert our Denary numbers into binary numbers in a way that's what the CPU, we're basically translating it for the CPU. So first things first, write out the number line if you've got your paper. So we've got 1, 2, 4, 8, 16, 32, 64, and 128. Got my number line there. A big misconception, people write it in that direction, but it's actually right to left. And if you notice, anyone can drop this in the chat as well, we're going up in powers of 2, like Charlotte said. So we're saying 1 times, we've got 2 times 1's there, 2 times 2, and going on 2 times 2 times 2, 2 times 2 times 2 times 2, we're going up in powers of 2, and that's on the screen there. And we'll try our very first one. It's already there. We've got 1 represented in binary. And how that works is, first we look at how many times, we're going to talk about switching on and off in a minute as well, but how many times can 1 be divided by 128? It cannot. It is too small, so we put 0. How many times can 1 be divided by 64? It cannot. We put a 0. How many times can 1 be divided by 32? It cannot. That's a 0. How many times can 1 be divided by 16? Still not. 8, definitely not. 4, definitely not. 2, definitely not. And then 1 into 1 is the 1 time. And the way I get students to visualize this is saying, if you've got 1 chocolate bar How would you share it with all these people? You could not, you could only, and it has to be shared equally, because some will be cheeky and say, I'll break it off into little bits, miss. No, you won't. It's one whole chocolate bar for one whole person. So now let's do that for 5 and then drop it in the chat. Let's all do that quickly. How would we do 5? And I've made it really simple, really, really easy. I'll write it on here so no one can see me. Put it on the chat now, as many people as possible. I'll put it here so we can all see. Why is it written right to left? In the same way that our denary system is written right to left, as we're moving up in powers. So the same way. So we've got 1 and then we're moving, making it bigger. So that's how our denary system works. We just replicate that in our binary system. Has anyone dropped the binary for 5? Did anyone understand yet, or should I still do it? Not sure. Okay, haven't seen the binary for 5. Okay, so 5 again, 5 chocolate bars, starting with 128 people. We can't share it with them. We don't have enough, so we drop a 0 there. Same for 64, same for 32, same for 16, same for 8. 4, we've got 5 chocolate bars. Yes, we can share that. So they can have 1 each. If we think about how many 4s can go into 5, it would be 1. And we no longer have 4 left because we gave 1 away to each person. So how many do we actually have left? We've got 1 times 4, 4 are gone. So we've only got 1 left, or you can just say 5 minus 4. So we've only got 1 left. Can we give 2 people 1 chocolate bar equally? No, we cannot. That's a 0 again. And then we've got our 1 and 1. So that would be 5. Yeah, show that on the screen, just like that, if everyone can see it. That would be 5. Okay. Brilliant. Yeah, it can be a little bit confusing at first. So I would say get your pen and paper. It will not work without it. So you can put your columns on there of your number line. So this is a number line, like your hundreds, tens, and units number line. And now we've done 1, we've done 5. I'm going to challenge you all, give you 2 minutes, really, really fast while I wipe my board. I've given you 98, giving you 255, I've given you 181. Drop them in the comments now. Be really, really quick. So start with your number line. Always start with your number line, makes it easier. Yeah, even in an exam, you can use your number line, so you're not penalized for that. Got our number line there. Start with your number line. Got some questions. Oh, some confusion before. Okay, that's fine. We will do 98 together. That's fine. It is confusing at first. And I relate it also to turning lights on and off. Which lights would you turn on to make your number? So if you had 98, if you turn the 128 light on by turning it on, by putting a 1 there, but the number's 98, 128 is bigger than 98. So I would say, yeah, so turn the light off. And I also say to my students, bigger or smaller? Bigger or smaller? If it is smaller, then it's going to be divided. If it is not, then a 0 will be there. Okay, keep popping those answers through. We've got 98 already. Has anyone done 255? Has anyone done 181? Let me just look at the time. We're doing okay. We're fine. We're fine. Okay, so just doing 98 there. It's definitely none there, 1 there, giving a clue to anyone who's kind of stuck so they can cheat in. Okay, time's up. So I didn't see a lot of answers, but I will go with the ones I did see. I hope everyone that's not typing is rather just quiet, not confused. I hope people are just shy, but not confused. Yeah. So we said we've got, Charlotte said, is it 011, 00010? Yes, it is. And we know this. If we write what Charlotte and Patience have written down, we know this. We can check it. We'll put the zeros there and that's another 0, that's another 0, and that's the 1, and that's the 0. And if you add this up, wipe this out, if you add them up, so I'm showing you how to turn binary back to denary now. If you add it up, 64 plus 32, these are the ones you've turned the lights on. The lights are on here, the lights are on there. So they're definitely involved. The light's on there as well. And if you add it up, you will see 96 plus 2 is 98. So it's definitely the right answer. That's how you can check. 255 is 11111. And that also comes to my next question then. What is the maximum number you can represent using 8-bit binary? And that's why I've put that 255 there, because we've only gone up 2 powers to the power of 8. The maximum number we can use with this method is 255 to represent. That's the maximum number we can go up to. If we want to represent more, we simply add another power. So we go to 256 and we go on and on and on. So the answers to the questions are right here. We've got 0110, 0010, we've got 1111 all the way, and we've got 1011, 0101. Does anyone notice a pattern yet in terms of the binary? If anyone notices a pattern, can you drop it in the comments what the pattern might be? So if we have got our denary, we might also be given some binary instead. So now we're converting binary back to denary. So number line again, don't know why I wiped it off, put the number line there. And we've got a number there that is 11000100. Okay, all it means is on, off, 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 on, off, off. That's all you just think about it that way. And only the numbers that are turned, the light bulbs are turned on, those are the ones we count. Okay, so we know that 128, the lights are turned on here, so we're going to put it down. Then 64, we don't need to bring all these really, we could just add 4 straight away because we can see that the light bulbs, the switch is on in terms of 4. So then if we add that up, it gives us 196. So I've got a few here for you guys to do. We've got 101, 00101, 101, 11100. I'll just leave it here. But the first one here in the number line, and I've got these 5 over here. Let's say a minute. Drop as many answers as possible. If anyone's confused at this stage as well, don't worry, some of these concepts, you have to look at them a few times to understand them. But I thought that representing numbers is just the easiest one to catch up. Let's see. Yeah, 165, okay. Well done, Charlotte. And there is a pattern. I'm hoping someone spots that there is a pattern with these binary numbers. And I wish I could say, well, I'll give you a box of chocolates, but I don't know where you all live. Okay, keep going. 1 more minute. Anyone that spots the pattern, there is a pattern. So one of the main aims this session was to get you converting binary to denary. So I just hope that we have gotten that part of it. Check again. Can't see the pattern at all. Okay, so Charlotte and everybody else, if you look closely, when it was 101, 00101, which is 165, that's an odd number. But the second one, where 0 was at the end, there is an even number. So whenever you see 1 at the end, then it's going to be an odd number. Whenever you see 0 at the end, then it's definitely going to be an even number. So that's another way to check that your answer is right. If you said 165, but it was actually a 0 at the end, then you'd know you've gotten your answer wrong. So I'll say that again. When it is an odd number, the last binary digit, it's a proper way to answer this exam question, the last binary digit will be a 1. And when it is an even number, the last binary digit will be a 0. So I'll just put people saying things now. Yeah, we see it now. Yeah, all makes sense. This will all make sense in the end, I promise you, when you look through the PowerPoints. So these are all the answers, a lot of correct answers going on in the chat box. I'm really impressed. 165, 188, 215, 230, and 250. And like I said, the pattern will tell us if we've got the answers right or wrong. Okay, so as human beings, we are very lazy. And we don't want to be reading a whole load of 111011010. No, nobody wants to do that. So if you look at this, we've got the binary numbers there, and then we've got another system that says C5. So it's taken an 8-bit binary digit, converting it to just 2 symbols. And human beings have come up with another base again, because we can have any base. I think it was one scientist saying that the concept of numbers and letters means nothing because they are just symbols, they're just scratchings. So whenever we as human beings want, we can create a different system and say, well, it represents this. So there is base 16, which is used by programmers in MAC addresses, in RGB colors. It's still binary digits, but the programmers don't want to read out those long numbers. So instead they came up with hexadecimal, so that way they could have simpler representations. By looking at the hexadecimal digit, they can convert it into binary. They know that's what it stands for. But for the CPU, it is still all the ones and zeros. So the hexadecimal system just simplifies how binary is represented. Each shall I say digit, each digit is a 4-bit binary, what we know as a nibble. So all we do is split that 8-bit in 2 and then get it to convert it into hexadecimal. I'll show you in a minute, it might not make sense. But in hexadecimal, we're going up in powers of 16. So we call it base 16. So the first digit will be 1, the next digit will be 16. The one after that will be 16 times 16. Okay, and that's how hexadecimal works, in the same way that binary and denary works. We've got a simple table. The main thing to remember is that we are taking parts of base 10, so the 0s to 9, and we're adding on new symbols. So these are not letters, they are just symbols. And these new symbols are A to F. So because we've run out of numbers to use, we've added on these symbols A to F. So 10 to 15 represents, because it's a 16 base digit, there need to be 16 numbers in there, but 16 symbols, if that makes sense. So that's why we've got part of the base 10 and then added on these extra letters, symbols. They're not letters in this case, okay? So for example, if we wanted to convert denary 231 straight into hexadecimal, we can. Using the same system, we will ask ourselves, how many times can 231 be divided by 16? I don't have a calculator nearby. Yeah, my maths don't have it nearby. But however, when we know what that is, it should be 14. 16 times 14, we would have a remainder, because 16 does not divide exactly into 231. So I believe that answer there should be 224 that we take away. We'd have 7 left. And that 7 on the chart is still 7. So we've got our 14 is not 14. 14 in base 10 is actually E in hexadecimal, if we look on the hexadecimal chart. So we've got 0 to 9, same, doesn't change. Then when we've got 10 is an A, 11 is a B, 12 is a C, 13 is a D, 14 is an E. So because 16 times 14 is actually 224, we've got an E as the first digit. So we wouldn't put down a 0. Remember, we'd put down a 1, or we'd put down a 0. Now we'd put down an E. And then for the 7 left, we would have 7. So 231 from denary to hexadecimal is E7. I hope someone's still following this. It's a lot of mathematics going on. Shall I explain it again? Is that saying explain it again? Okay, makes sense. Good. I'm happy it makes sense. So that's the first one in terms of denary to binary. And then converting binary to denary is to hexadecimal, sorry, is even easier than that, because we take an 8-bit binary like this one, we split it in 2. And now because it's 2 separate nibbles, we change the column heading. So rather than going all the way to 128, we would now have 1248 and 1248. Okay, we're just splitting that table in two. It's still the same and binary digits moved over. And if in our first nibble, we've only got 8, in the second nibble, it actually adds up to 13. So this one is 8, this one is 13, okay? So going back to that hexadecimal table, we've got 8 and 13. Can someone just drop in the comments, what hexadecimal would that be? No, I've put it wrong way around. Show you that table. What hexadecimal would that be? We've got 8 and 13. What would be the hexadecimal for that? Just drop that in there. Remembering that we go up to 9. A, B, C, D, E, F are 10 to 50.
Right, put it here.
Brilliant. 8D. Good job, Patience. Fantastic. Because the 8 came first in that nibble of the table, and then the 13 came after. So we would have 8D, okay? And that's how numbers are stored in binary. I'm meant to be moving on to how text is stored in binary. I'm hoping everyone is still here and I haven't lost anybody at all. So I'm just going to be like, whoa, I'll just do a little shaku, you know, so you're still here. I'm doing this on YouTube to encourage those on YouTube. Do a little dance so you know you're still here. We're all still here before we move on to how text is represented in binary. We're done with numbers. We looked at binary. We looked at denary. We converted denary to binary. We converted binary to denary, and we looked at hexadecimal. So we're about to go into text. Before we do that, let me have a quick look at the chat. Still here, yes, Oyin, I'm so happy with that. Okay, so in terms of how text is represented in binary to computers, remember again, they're just symbols. The computer doesn't know that these are numbers, this is text, doesn't know that. So all we have to do is agree. Once we agree on a code, I don't know if anyone did the Caesar cipher back in secondary. When you're talking about cybersecurity, there's a Caesar cipher. And Julius Caesar basically came up with a code that was 3 numbers up from the letter. So if it was D, then it was like EFG, so G. So that's how he encoded messages. So when we encode, we're agreeing together. Not always together. Sometimes different countries have a different encoding. I don't know if people sometimes have like a Japanese keyboard, then there'll be different symbols somewhere else. That's what happens when we don't agree together. So when we agree together, we will say this symbol should actually be attached to this binary code. That way, the CPU can understand to output it to us. We need to program that 01000, whatever that is, might be 65, that might be the letter A, for example. We all need to agree. So the first set of people to agree, apparently, were the Americans. So they had ASCII, which is the American Standard Code for Information Interchange. And all they were trying to do was represent the Latin alphabet. Okay, they did not use 8-bit binary, they used 7-bit binary. And again, like I said, a lot of these concepts, they're not from a long time ago. If we look at 1963, that's barely, 57 years ago. So there are people that live before this was invented. So 7-bit binary, they would agree that, okay, the number 65, if we convert that, we're going to wipe out 128. From our number line. So we're stopping at 64 now because it's 7 bits. How do we know it's 7 bits? 1, 2, 3, 4, 5, 6, 7 bits. And if we say 65, 65 would be equal to 1, 0, 0, 0, 0, 0, 1. And then we can agree and say this is actually a capital letter A. So that's how they developed it for encoding the Latin alphabet. But then there's an issue, isn't there? Because there might be, if we look at the maximum number we can represent with 7 bits, all we have to do to know the maximum number is add all these up at the top. And if we add them up, we will see it comes to 127. So if we can only represent 127 possible combinations, for example, and throwing that even extra 1 bit to 128, how will we represent emojis? What about the other letters in Russian? What about Japanese symbols? They did not account for that. So this is the ASCII table. It shows exactly what symbols are what in decimal. So we've got, and remember as well, A is capital A is a completely different symbol from small letter a. We recognize it as A, but the computer just sees it as scratchings on a page. So it just sees it as a symbol. It's not a letter, it's not, it doesn't know which is which, apart from when the ALU does the mathematical calculations. So this is the table here. Just have a close look at it, because I'm going to ask you then, you know what I'm going to ask you to do, to convert binary to a letter. So what letter would that be corresponding to, or convert, so convert ASCII to a letter. Got a question there. We're learning a lot. That's good, Panama. Thank you so much for saying that. I feel a little bit bad because I'm making people learn a lot this evening, but this is what you signed up for. So we've got the ASCII table. Capital A is 65, small a is 97. It's different. We've also got exclamation marks. We've got the pound sign. We've got the, ampersand as well. So we've got all those different characters and symbols represented. And once we agree that, for example, let's look at what F. So we're saying F is 70. And we can convert that then to binary. So we know what to program the CPU with, so it knows that that is a capital F. I've already spoken about the limitations of ASCII. And if we just have 7 bits, then we can't represent emojis, for example. So what is the solution? They came up with Unicode, which is 32 bits. It can store a lot more characters. It's got more bits. So if we do 32 to the power of 2, it's got so many, so much more so much more data that it can store there. We've also got UTF-8, which combines ASCII, and it saves each character in its own memory location. So then we can do unlimited, and that's why we've got emojis. That's why we can represent all different types of symbols. Initially, I think it was the Japanese, they couldn't agree on the encodings. And what happens is when we don't agree a universal table or universal understanding, when you take it from one computer to another, it will not recognize it. Even when you're programming, if that compiler is not present on another CPU, your great, nice game app is not going to be compiled properly, because we've not agreed that this is the standard set that we are going to use, okay? And so graphics, looking at the time, graphics in binary are also still 0s and 1s, okay? So each little bit on this grid, so we have a grid. What I say usually is just draw a grid, which I'll do now. So if we draw a grid, it's like a table here. We'll do, I've done it wonky, done a wonky grid. Draw a grid. Yeah. And if you look at this grid now, you see we've got little squares on the grid. It's got 1, 2, 3. We've got 9 spaces in here. So this is like a 9 by 9 picture, what we call metadata. So each square in this grid has a 0 or a 1. Okay, and this is how we represent black and white. This is called pixels, picture elements. So when you're seeing those fancy HD TVs and everything, we're looking at picture elements. That's called pixels. So how many pixels can we pack densely into these grids will improve the quality of what we see. So images too have to be converted into binary. There's a really nice unplugged activity where you can shade it yourself, and you will see that you're making a picture by shading the ones with a 1. 1 still means on and 0 still means off. Okay, so we shade the bits with the 1 and we leave out the bits with the 0. You can create really nice pictures. You can try it yourself. You can create a smiley face. I'll probably drop that as a link for Charlene. I'm really mindful we're running out of time. And if we want to add more color to this, then we add more bits so we can store more pixels. The more pixels you can represent on that grid, the more bits you have, the better the quality. However, that means higher file size. And that's why you see when we've got improved functionalities on iPhones or Samsung, we're losing more of our storage space because now we've got a higher file size. So when people say, oh, my memory on my iPhone ran out, well, you're taking better quality pictures and you're taking better quality videos, you're using up more pixels. And just really quickly then, we'll look at how sound is represented. We won't go into logic gates. The simple explanation as well is that sound is also converted into binary. The long and short of it is that the microphone, which is the input device, collects the sound and then it's recorded, it's sampled at various intervals. So it looks like this. The normal microphone sound are all the green bits, and the computer version where it's mapping each sound at a certain time are the purple bits. And you can see that this digitization, because we call it an analog to digital converter, we have to have that in our computer system so it converts the sound into digital sound. You can see it doesn't match up exactly. And why is that? Because we need, again, more bits so we can store more at precise points, which will then improve the quality of our sound, but then in other words, then increase our file size. So that's how sound is represented in really, really real basics. The sample rate is the number of samples of the wave that are taken per second, as we can see here on this graph. And then we've also got the sample interval. So how much time do we leave for each sample? We've got some questions there. I think this is the last part about how data is represented. I'm not going to do logic gates. I'll have to send the logic gates through. I'll have to go in detail onto the PowerPoint to cover so many things. We were meant to do a binary spinning the wheel. Should we still do it? Because I do want to check that people understand, or should we go to questions? Charlene, I think you be the judge of that. Just before I go, sorry, carry on.
Let's do the binary spinning the wheel. I think that would be really good to do.
Yes, let's do that one. Before I go really quickly, if you want to contact me at any point, Charlene will have the PowerPoint, but basically I'm on LinkedIn, I'm on Instagram, and you can email me as well. There is a lot of extended learning. I hope I come back to teach you some of this because I'm actually really excited about it, if that shows. We're going to go to the spinning wheel now. And we're going to convert numbers into binary. So I'll just spin the wheel, whatever it lands on. If it lands on binary, we're going to convert that to denary. If it lands on denary, we're going to convert that to binary. The best part is I've got an actual spinning wheel. So for the sound effect, I'm going to spin my actual wheel. But if you can see, I've got my actual spinning wheel with you in spirit. I'll spin it as well. Got it both. So 113, that is the denary number. Can we convert that to binary and drop it in the chat? Convert 113 to binary. Let's do that now. What do we do first? Put on our number line. Someone already got the answer. What is the answer? It's definitely 64 there, which is a 1, and 32 there, which is a 1 as well. 0, 1. That's 98 already. I'll go with the benefit of the doubt that people are putting the right answer. Oops. There we go. We got answers in there. Oh, you should be dropping the answers. Thank you so much. So we got 1111001. It cannot be 1 because it was 113. So that would mean you're turning 128, you're turning that switch on. So definitely 128 is already bigger than 113. Yeah. So we would actually turn that off. It'd be 0, 1, 1. Who else has the answer? Come on, somebody put the answer in there. So we take 113 from 98. So we can move to the next one. What have we got here? 1 here. 11. So it's definitely not 16. It's 1 on the 8. We've got 3 left. Yeah, so we should have 0, 1, 1, 1, 0, 0, 1. Not quite either. Ooh. Well, somebody else has the right answer there. 0, 1, 1, 1, 0, 0, 1. Are we on the same number? We're on 113. Okay, let's spin it one more time. This time, I'm just going to show everyone how to do it again, because I've noticed we're not sure. Okay, this one's easier. This is easier for us. This is converting binary to denary. So put the 1, 1, 0, 1, 1, 1, 0, 0. And all we're going to do is add it up. We're just going to add up the numbers that the switches are turned on. So I'll give you guys a chance to do that. You're just adding it up. I'll add it up on mine. 128.64 is 192 plus 16. You can use a calculator as well and probably get there before me. And what's the answer there? 220. And we can check that because there is a 0 at the end. So we know it's definitely going to be an even number. Should we do one more? Are we okay? Are we excited yet? Should we do one more? For converting denary to binary, I lose track of what I'm supposed to be subtracting, but the other way around is much easier. Yes, that's true. So let's spin it and see if it lands on denary, and I will help out. 13. That should be an easy one. It's got 13. What we're doing is working from left to right. We are checking 13 suites. Can we share it up with these columns, with these, let's pretend they're kids. So we've got 128 kids. No, we cannot share 13 suites with 128 kids, or with 64, or with 32, or with 16. So straight away, we know we can share it with 8. Easy peasy there. We can share it with 4, none for the 2 children, and over there for 1. And that would be the answer for that one. So that's how we'd work it out. Yeah, you can do a 4-bit. If you did someone's done a 4-bit, yeah, 1101. You can do a nibble. You don't have to do the whole 8 bits when the number is smaller. So that's good. And no, I don't want you guys to do a binary. I want you to do a denary. Oh, it's not choosing what I want. So I just choose a number. The spinner's not following me. 180. Let's do 180 because I've spun it over and over again. Let's do 180. 180, let's convert that. I'm just checking that people understand. Let's convert 180. And Charlene, I just want to check, are we finishing at 8 or 8:30?
I think we can go on to 8:30. So
yes,
yeah, we can absolutely do that. If people would like to stick around until 8:30, feel free to stick around. Obviously, if you have to leave, that's okay as well. But I think it's fine to go on 8:30.
Yeah, if you want to stay, we can look at some logic gates. I know that doesn't.
It's amazing.
I know that doesn't sound like the most, but we can do this. Is logic everyone staying? Yeah, logic gates are fun. You're right, Charlie. Yeah, I think people are staying. Okay, let's crack on then with logic gates. I'm happy about that. Thank you for that. I've got a bit of excitement now because we're going to do my favorite topic. So quickly looking at logic gates. What is logic? It's just true or false decision. We have to make decisions. These are usually true or false. So easiest for me, is it raining outside? Yes, grab an umbrella. If it's not, no, you don't need to. Will you be getting the bus? Maybe you need to get your bus pass then. All these logic, we think using logic. And the best thing about computer science or computational thinking is we don't realize how many different logical decisions we're making. When we break them down into smaller steps, then you're like, oh, wow, in just getting ready in the morning, in fact, in just brushing your teeth, you're making so many logical decisions. And the computer has to do the same. It takes a lot of electronic circuits to make these decisions. So it looks at with Boolean logic, which was invented by George Boole, he's a scientist as well, or a mathematician. It looks at the inputs that are being given, so then it can determine the output of the circuit. And there are different types of logic gates on the CPU, so that's why we're looking at this. So on the CPU, we've got logic gates. We've got circuits on there. So it's got to look at, what is this electrical signal? Is it on or is it off? And how should I respond to it? Okay, so the process of doing this, sorting out this electronic logic, is called gates. That's why we look at logic gates. So there are different types of logic gates, like I said, on the CPU. We've got the OR gate, we've got the AND gate, we've got the NOT gate. And if you've simply been and there are also 3 different but equally powerful methods for describing each of these gates. We can do it in truth tables, we can do it in logic diagrams, we can do it in Boolean expressions. I'm going to show you some logic diagrams as well as some truth tables, because I think it's easiest to see the diagrams and then it makes sense. Okay, so the very first one is the AND gate. Just wipe this off. It's on the screen. And in drawing the AND gate, it's like a circular shape. And if you notice, we've got 2 inputs. So we're getting 2 electrical signals here to determine an output. So that's what's going to happen on this circuit. So based on the inputs, then we would get a certain output. For the AND gate, it has to be that both inputs are true for the output to be true. So pretend you were going, I know this is pre-corona, you were going to the club with your friends. Are you wearing the right dress code and are you wearing shoes? If you are doing both, you can enter. If you're wearing the right dress code but you're wearing trainers, obviously you cannot enter. And there's very different scenarios that we can relate this to as well. So if both inputs are true, then the output is going to be true. If one input is false, then the output is going to be false, because we've said A and B, not just A on its own. So that's the AND gate here. And we can signify that in a truth table. Just draw one quickly. We've got A here, we've got B here, we've got Q there, Q there. So we've got A, B, Q. So if A is 1 for on and B is 1 for on, then Q will definitely be on. But if A is 0 and B is 1, then automatically, because it's now false, we said A and B must be on, then Q will already be 0 automatically. And likewise, if A is 1 and B is 0, then Q will also be 0. So both must be on for the output to be on. So that's one of the important gates. The truth table's there. I just drew it, but it's there on there for you to see as well in the PowerPoint. And then we've got the OR gate, and I think about it as a circular kind of arc. I drew it like this to make sense. And one of the inputs must be on. So now it's not both. So you've either got this or you've got that. Okay, and then the output itself will then come on. So if A is on, then B is off. Q will still be on because it's either or. If they're both on, Q is still on as well, because as long as one of the inputs is on, the output will be true. So both are true, the output is true. And we've got the truth table there. Like I've said, A and B both off, both false, the output will be false. A is false, B is true, the output will be true. Let's flip it the other way, and then if all of the inputs are true, the output will also be true. And then we've got what I call opposites day gates, which is the NOT gate. It's saying not the input. So whatever the input is, it will do the opposite. If the input is true or 1, it will change it to 0. The output will be 0. If the input is 0, then the output is 1. And these circuits, they're very important. We use them in a lot. We use them in monitoring. So like sensors, we can check, is the room temperature this? Is the light on? Turn on the heating. This is used in a lot of electronic devices, not just computer systems. Got a question already. Oh, coming to it once I can get this up, which I'm not a zoomer and it shows. Yes, it is yes, it all connects together, all the programming, everything connects together. So logic gates are used to build complex logic systems such as burglar alarms, heat sensors, and all we do is we take the basic gates that we have and we actually just join them up. We join them up to create more complex gates, okay? So what this will look like in a diagram is like this. Yeah, so we're saying there's a NOT gate, A, NOT D, B and C together, and that input is now D and E to give an output at Z. That's what we're saying with this diagram. We've actually put the 3 gates together, a NOT gate, an AND gate, and an OR gate as the output. So if we look at this diagram closely, if the input at A is true, what would be the output at D? Just to check that people are following. If the input at A is true, that's a 1. What will be the output at D? Just pop it in the chat. Fantastic. It will be a 0. Great job. Yes, because it's opposite states, it will switch it over. And if both of the inputs at B and C are on, then the output at E will be what? 1. Good job, Charlotte, Louise. Very, very good job. Good effort, everyone. And I've actually denoted that here so we can see clearly. If we turn all the outputs on, then we're going to have a 0 over at D, a 1 over at E. What would we have at Z then, which is the main output we're looking for? What would we have at Z? We're now at the OR gates. Good, I've got some answers here. We would have a 1. Fantastic, because it says OR. So either E is on or D is on. Either one will work. If both are on, fine. If one is on, fine. But if both are off, there will be nothing for our output. And I think at that point, most of that logic gates is covered. So the knowledge check was that we wanted to know the principles of von Neumann architecture. I hope I've been able to explain that in as much detail as possible. Simply the idea that data and instructions are stored in RAM, fetched by the CPU to be processed. We needed to explain the functions of the CPU. We've said that it processes the data, it fetches the instructions, decodes it, and then executes it. And we talked about the different components, the control unit, the arithmetic logic unit, and the registers. We didn't really go into cache for now, which is something we can look at as well in the future. We needed to be able to discuss stages of the Fetch-Decode-Execute cycle. So what's happening in each phase of it. And now we know how numbers are converted in binary. We briefly went over how text is converted in binary. We looked very, very shortly at sound. The sound one is actually quite in depth that we could cover. We've also got graphics as well, how they're represented in binary. We have been able to convert binary to denary and vice versa. And I'm really happy that we all did that together. And we now know the difference between what we program, high-level language, and what the CPU understands and the steps that it goes through to have to compile that over, or if it's assembly code, then it's its own assembler that it uses. So I'm happy that we've covered a lot of that in as quick as possible. If we wanted to look further, you could look at memory and units of storage, You could look more into the mathematical aspects, because we only talked today about how positive numbers are represented in binary. But when we want to add, subtract, deal with negative numbers, there are other techniques and methods we have to use. In fact, that's a whole lesson in its own that I always love doing. How sound is represented in binary, like I said, we can go in depth with that, and how graphics, and then how the operating system itself works, because it's not the boot sequence, that's separate. So the operating system is not stored in ROM. Okay, so we can go into looking at that for extended learning, computational thinking, which is one of my favorites, writing algorithms, especially search and sort algorithms, which I think are actually the foundations of algorithms, and then looking at translators, compilers, and interpreters. So I finally got to the end of it. I've got a lot of useful links for people who want to learn computer science without teaching it, or sitting there the whole day doing the degree. I think Tech Quickie is a really good one, because in very short terms, one of my favorite one of theirs is how data is transmitted across networks. And it gets you thinking, shall I go interrupt my Wi-Fi because of the waves, the signals that it sends, or how data is sent undersea by cables. They've got some really interesting concepts there, especially in relation to networking. I don't know if there are any potential networks engineers. You could look at those videos as well. They're really, really interesting. Got some. Oh, who says your oldest is in year 9? Is that to me? And how did you know that? If that's to me, who is that? Oh, okay, good. Because I would have been like, oh, okay. Yeah, so Charlene, I think at this point, I've kind of covered everything. If you want to take over, if anyone has questions to ask me, I'm happy to answer them.
That was fantastic. Thank you. I know that a lot of people found that really, really valuable, and that they really enjoyed the session. So thank you very much for that. Does anybody have any additional questions? Everybody is saying thank you, that they found it.
They're like, let me go quick before she starts again.
They absolutely loved it. So thank you very much.
Thank you very much.
When is the next lesson? We're definitely going to have another one. If you'll come back to us, then we would love to have you.
100%.
Oh, amazing, amazing. Thank you so much. Absolutely amazing. I definitely remembered a lot of the things. Well, I didn't remember them. I learned a lot today. There was a bit of a refresher. So thank you very much for that.
Oh, anytime. I actually also want you guys, I want to thank Charlene. A lot of people might see this recently, but I didn't have this in the past. I'm really happy to be part of this community and have this opportunity. When I started out in 2013-14, I was usually the only person that wanted to talk about things like this, so I was a loner. And now knowing there's more people like me out there, and Charlene's brought us all together, you're a legend, Charlene.
Thank you. Oh, that's lovely. And the work of Coding Black Females and Neo Enterprise, bringing the boot camp together and bringing so many Black women together to do so many awesome things. It's amazing. And I'm glad that I got to meet you as well, because I think I saw you speak and I was like, I need to know you more. So thank you very much. Thank
bless you. Thank you so much. So should we let everyone go then and be free?
Yeah,
Friday night,
go away and have your dinner and have an evening.
Yes. Go and shaku. You need to do that. Have a good night.
We could end the evening with some of your Afro beats.
Oh yes, let's do that. Yes, happy days. If people were going to turn their camera on, we could have had a little selfie as well.
Ooh,
if anyone wants to join in, shall we do it?
If you stop sharing,
first.
Yeah, stop sharing, and we can get everybody on screen.
Let's get on screen. Let's have a little.
Amazing. I'm
seeing. As a teacher, I don't get to wear any makeup, so let's preserve this moment for the history to see. Is everyone ready? How do I see a gallery view? Yeah.
Yeah. Can you see it?
Yep. Yay. Yes.
Are we going to get some more faces tonight, ladies?
Come on, let's go in it.
Nice. After our Friday night of computer science. Love it. Awesome. I'm taking a photo as well.
Okay. Can you hear that? Can we hear that? Yeah, let's go for it. Hey, hey. Why is it only me? Where's the rest of you? Okay, do you know this one? Test, test. Oh. Turn it up. I can't help myself. There's a leg work for it. I don't know. I can't do it right now. Oh, you know about this. You know about this.
Yes, I do. Got to.
Okay. Should we? Yeah. I'm just gonna turn it. We're all in the sitting down mood, so hit me up for any of the dancing, all of the Afrobeats. I'll be there.
If we were in person right now, the lights would be up and we'd be dancing right now. So
definitely. I tried my best, YouTubers. I did my best, so can't fault me. But really, thank you again, Charlie.
Thank you so much.
Oh, last thing, thank you, whole group. You picked it up so quickly. I've taught this to GCSE computer science students, and they're like, I didn't understand any of that. So thank you. Well done. A lot of people, I should say thank you to all of you for following those concepts. Well done. You did really well as a group, and I hope to teach you again.
Thank you so much, Tessie.
All right. Good night, everyone.
Bye, everyone.
Bye.
Have a lovely night. See you all soon.